Okay, this question is very uh, important as in terms of application of optimization, and how you can see the power of optimization in doing statistics. So suppose we're given a lot of points, x1, y1, up to xn, y, and n could be really large, could be 1,000 or so. And the x1, x2 are the x1, x1, y1 will be the first pair in your data. So the purpose is to find a line that can almost pass through these points. So what that idea is this. So let's suppose this is x, this is y, and you observe lots of points. For example, this is the x1, y1, x2, y2, x3, y3, x4, y4, so on and so forth. So we're trying to figure out a line, straight line that pass through all these, almost pass through all these points. So what's the best line to fit them, to fit this data? So the line is determined by the intersection and slope. So the intersection, we say this, the intersection is A, the intersection is B, and the slope is A. Then this line will be AX plus B. Okay, the question is what are the best A and B here to fit those points? So we need to give a criterion by fitting what that means. So the fitting means that if these points if the line is really ax equal to b, so then I plug in xi, yi, then the axi plus b should be similar to yi, right? If y is really on the point, on the line. But in practice, there will be some noise so that the points may be slightly off the line. And the purpose here is that if there is some discrepancy between axi plus b and yi, then I will check the difference between them, and then the smaller this value is, the better the line fits. But the line, there's only one line to fit so many points, so we cannot satisfy everybody, right? We have to see that if the total error is minimized. So by total error, I mean that this is the discrepancy at the one single point pair xi, yi, and we take the square to just avoid doing negative values, since they will cancel out with others. So we square them. So that's the squared error, and then we take the sum of these errors, squared errors at every point. And then we normalize it by 1 divided by n, just to normalize things, but this is just a constant, doesn't affect our choice of a and b. So we want to find the a and b so that the total, the sum of the squared errors is minimized. Okay, so that's the idea. So we want to find this a and b that can minimize this f. The question gives us some constants or short notations. They say the x bar means the average of xi. Okay, just take this average of the xi's. So the y bar means the average of y. The x squared bar means the average of x squared. So it's the average of xi squared. Okay, and also the y squared is this. And also xy bar means the average of the xi y's. So take the sum of xi y, then average it. Okay, and the first question is how to write this function f in a quadratic form. It's not surprising this is a quadratic function, because look at here, just look at each term. It is a quadratic function of a and b, which are the unknowns for a problem. And so this should give us a quadratic function of a and b, and take the sum and take some scaling of 1 over n is still a quadratic function. So we have a quadratic function of a and b. So the question asks us to find out the standard form of this quadratic function. And for this quadratic function, if z is a and b, it's the variable we want to solve, then the q, once we can determine the q, c, and d, then we can consider their minimization problem, since it's just converted to a problem of z now. So the question is, how do we write q, c, and d in terms of these quantities? Okay, so that's the first question. The second question is, suppose all these xi's are not equal, so at least one of them is different from others. Then the question asks us to find the optimal point a star b star, the optimal value of z, which is called a star b star, so that and also asks us to show that the A star, B star will be the only possible local minimizer of F. And the last question is to show that the relation between these 2 points, A star and B star, if they are optimal points, then the A star, B star should satisfy this equation. Okay, so let's go through this one by one. So the first question is to find this quadratic form. So how do we write this thing here as neat as this? Okay, so how do we get that? Assuming that Z is equal to, Z is a two-dimensional vector with A and B as components. Okay, to do that, let me show you this. So let me give you a new notation M. So the M is this matrix right here. So remember that the x1, x2, x up to xn, so it will be really, really tall, and a tall and thin matrix because it only has two columns, but has n rows. The n is the number of points we have, could be thousands. Okay, and the y is just the vector, y1 through n. So the y1, so the y has the same height as m, right? So now we can rewrite this thing into this neat form. And why is that? So the reason is you look at this axi plus b times y. So what that is? So this is actually just suppose I have, look at this matrix. Suppose I have the A and B here, and just look at the first row. When I multiply these two matrices together, or this matrix and vector AB together, on the first component, I will get AX1 plus B, right? And correspondingly, I will have the Y1 here. So this is the Y1. So that means when I multiply this row with this vector and subtract the Y1, that will be my this term here for the first component. Okay, and similarly, I can do this for the second component up to the last component. So this is essentially taking the norm of this matrix and this vector minus this vector. So the difference of this vector and this vector. Okay, that is what this norm is, because you're taking the squared sum of the squared components. So that's essentially the squared norm of that vector, and that vector is just the m times this AB vector minus this y vector. Okay, so once you observe that, then the things will become easy. Okay, so let's see. So the f of x AB will be just the f of z, because the z is a new notation for A and B, and we say that this is just that. So the 1 over n of the left-hand side is just 1 over n of the right-hand side. That's just this. And this is much closer to the quadratic form we want. And to get that, we just need to break this parenthesis, break this norm. So we know that this is the inner product of this vector with itself. So that will be just the vector here. Put that as a row, as the original vector, as the column vector here. And then we just break the parentheses. And we have the 1 over n, which is still here. And then the inner product of the 2 here. So that's this. And the interaction term, and also the last term for y. So that's all we need. We just need to verify that this is the quadratic function of z and see what are the corresponding components. So now you can see that if I multiply the 1 over n and this m transpose m, that's my q. That's the q needed in the question. So slightly different from the standard form where we need a 1/2 in the front, but it doesn't matter. 1/2 is just a constant. So for the question they want just that. Sorry, they just wanted the z transpose qz, right, plus some like bz. So they call it c transpose d, z plus d, right? So we need to figure out the q, c, and d here. So that's my q. Okay, and this is, sorry, including the negative. This part and this will be my c, or I should say c transpose. And this times this should be, or d, constant term d. Okay, I think they have the negative suit c, so that should be, which is the remove the negative 2 part from the c, so that's our c. That's the d, and that is our q. Okay, so now we just need to rewrite the q, c, and d in the 5 constant or 5 shortcut notations we used, or the problem defined. Okay, so let's see how do we do that. The Q is the 1 over n times m transpose m. So this is the m, right? Remember that. This is the m transpose. So when I multiply the 2, I know that I'll get, since this is a 2 by n matrix, 2 by n matrix, this is n by 2 matrix. So when I multiply them, I should get a 2 by 2 matrix. So what that matrix is this times this. That gives me the first component, first entry. Okay, and you can see that just the sum of the xi squared. Similarly, this times this gives me the second entry, and also this third entry, and this is the last entry. And then we can see that's just this. And when I put this 1 over n inside onto each of the entries, I will get just the average of the xi squared, average of x, and average of n, which is just 1. So that's how we get that. That's the Q matrix. And then the C matrix is similar. So we just multiply this and this, right? That's the M transpose. This is the Y. And then by simplify that, we'll get this. Okay, and similarly, we'll get D equals to that as well. Just easy to verify that by yourself. So that's all for the Q, C, and D. Then let's finish the first question. Second question is to show that the optimal, assuming the xi's are not are not equal, then we want to find this optimal point and show that it's only possible local minimizer. Okay, so remember, why did xi's need to be not all equal? Remember that from the picture I showed you here. So the xi, y's are given points in this graph, right? If all the xi's are the same, that means, say, if all the xi's taking this value, specific value x1, they're all equal. So that means your y just like, your points are just like this. So in this case, there's no way to fit a line, right? You can use any line because they are all on the vertical. These data are on the vertical line here. So it's impossible. And from linear algebra, we also see why that is necessary. So remember, we want to find the optimal point. So we just need to check the first order necessary condition and see if any point satisfy that. And then we want to further show that it's only local minimizer. So because there's no constraint on A and B, so this is a totally unconstrained problem, and A and B, if we found a open point, it must be an interior point. So the first order necessary condition is just that gradient of f at this point is 0. Okay, so the gradient of f at that point is 0. You see that? This is the f. So the gradient of f will be just taking the gradient of that. So we did the standard form, but it's pretty easy to do this one here. So if you like, you can do this 1/2 and 2q here. That doesn't change anything. And you treat this 2c transpose as the b. So then we have a q, z, 1/2 times z, 2qz minus some vector, which is 2c here, times x, plus some constant. And this constant d doesn't matter. So take the gradient, we'll get that. Okay, and solve for the z. So that's z star, which is the a star b star vector, should satisfy this, and also for the z, which is this q inverse times z. So the a star b star, which is the z star, and that's q inverse times z times c, and the q and c are something already calculated in the first part. Okay, just put them back here, and then you compute them. You have the inverse of that. So the inverse 2 by 2 matrix is something you always should be familiar with. So suppose we have UVWZ inverse, it should be equal to the Z, negative Z, negative U. Oh, I'm sorry. So it should be, let me use a simple notation. UVWZ, the inverse of that should be Z. You just switch the location of diagonal entries and then put a negative sign on each of these off-diagonal terms. And then I need to divide this by its determinant of the original matrix, which is UZ minus VW. So that is the inverse of a 2 by 2 matrix. Okay, so this is something you might want to know. For high dimensional, for 3x3 or higher, we don't know how to do that. Okay, we know how to do that, which is we don't do that by hand. So you use computer. But for 2x2, we can easily do it by hand. Okay, so that's this, and then you calculate this, you end up with that matrix or that vector. So that's our optimal point, A star, B star. So apparently there's only one point that can satisfy this, because the Q, remember the Q is this x1, xn, the y's, right? So because all the x's are not all equal, so that means these two columns are not linearly dependent, right? The first column is not some multiple of the second column, which are ones. This means that this matrix M actually has a full column rank, which is 2. So in this case, if it has a full column rank, and M transpose M, which is 2x2 matrix, should be full rank, and that be a rank 2. This rank 2 means that the Q is invertible. Okay, and the invertible means that the Q inverse times that's only one determinant function. It's only one possible value, or that means this one can only have one solution because Q is full rank. Okay, so you just cancel the 2. Then you need to solve the Q z star equals to C, and there's only one possible solution. Okay, because Q is invertible. Okay, so that's only one possible. And the last question to show that A star, B star satisfy the relation, this equals to Y bar. Okay, so just plug in values. A star, B star is these two components. So this divided by that is the A star. This divided by that is the B star. Plug them in, we'll get just see some cancellations. So I think that's straightforward computation. I don't have to go through. Okay, so you can easily see that. But the point is that you can see what this means. So the x bar is actually the average of x. The y bar is actually the average of y. So that means when we find the optimal point, A star, B star, it definitely makes that the point x bar, y bar to be on the line. So that means we have this x and the y. Sorry, this is the x, this is the y. So we have bounce row points, right? And then we have this line. So this line guarantees that if you take the average of those x and average of those y, you get a single point, and that single point must be on this line, which is x bar, y bar. So that must be on this line, optimal line here. Okay, that's the question.